Okay, so we'll go through the AY1920 quiz one first. All right. Okay, so the first question is on the battery as well as some understanding of C rate. All right. So as you can see over here, we are given that the discharge, what is the discharge current, okay, of a 14.4 watt hour battery operating at 2.4 volts and 1.6 C. Okay, so now if I say that this is the battery power rating 14.4 watt hour, which means in 1 hour I can provide 14.4 watts, correct, of power. So that means the current, all right, if I'm operating at 2.4 volts, all right, the current that can be discharged in that same 1 hour is 14.4 divided by 2.4, which will give me 6 ampere. All right, so this is the amount of current that will be discharged, okay, in 1 hour. That means if I operate in 1C, right, if I operate in 1C, but now I'm operating in 1.6C, all right, which means that the amount of current is supposed to be higher, right, supposed to be higher. So in 1.6C, it will be 1.6 times 6, which will be 9.6 ampere. All right, and that is 9,600 milliampere. Okay, which is option C over here. All right. So as long as you understand the relationship, okay, between the power rating, the voltage, and the C rating, then this question, I mean, the past two papers also you have seen some similar question. All right, so you roughly know what to expect. All right, in terms of the type of questions that you'll be asked. Okay, so I will just carry on. All right, actually all the answers are also given to you, correct? I mean, but the only answer you have is the actual option, correct? The explanation is not given. So that is what we are going through, all right, today. So to make sure that you actually understand why we have selected these as the answers. Okay, so the next question. So this is on battery design, okay, and it's quite a standard process, correct? If you look back at the studio handout and what you did in the studio as well, it is quite a standard process. So here, basically you do it step by step. So we know that the midpoint voltage for battery is 3.65 volts, all right? So the first step is we start with that, correct? We start with the midpoint voltage based on the instantaneous C rate that is required. And from there, we look at the required operating voltage. All right, and that would be the first step. So 13, which is the required operating voltage, divided by 3.65 will give me 3.56, correct? And then you take the ceiling of that, which will give me 4. So that is your number of cells in series. Okay, so I need to connect 4 cells in series to provide the required voltage. Right, so the required voltage, that, I mean the voltage that will now be supplied, okay, by the system is 4 times 3.65, which is 14.6 volts. Okay, some of you all have asked me this question. When we take the battery selection based on the instantaneous C rate, your voltage that you get is actually higher than the required operating voltage. So is that an issue? All right. So that is not an issue because all electronic systems, okay, when you design them, you will have what we call a voltage regulator within the circuit. Okay, and that voltage regulator will make sure that whatever voltage you supply, even if it is higher, it will sort of regulate it down to the required voltage that the system requires. Okay, so a voltage regulator, you will actually be seeing that I think quite soon in one of the studios. Okay, and then you'll see how it works. Any voltage that I provide in, okay, depending on the rating of the voltage regulator, you actually step down and give me the required voltage. All right, so even if my supply voltage is higher than what I want, it is fine. All right, but that is just for you to understand why this is okay. All right, so it's not going to cause an issue. All right, so the system can be designed to step down, all right, to the required voltage for the rest of the systems to operate, all right. But when we're doing the battery design and the calculation, we still take this in our calculation, all right, because that is still the output generated by the battery, all right. Okay, now the next thing is in terms of the efficiency, okay, and systems. So in terms of power efficiency, we have three systems. Okay, what is important is to understand whether the systems are connected in series or in parallel. Okay, if you look back at the notes, series is different formula, parallel is different formula. All right, so in this case, we can see that each subsystem requires 20 watt. All right, that means the calculation has to be done individually. All right, so if you were to draw each subsystem out, okay, each subsystem, so one is 90%, the other is 85%, the other is 94%. All right, and each of them is 20 watt. Correct, each of them is providing 20 watt power. All right, that means the input power to this would be 20 divided by 90%, and this one will be 20 divided by 85%, and this is 20 divided by 94%. All right, and then I need to add them up together, and that will be my power in. Okay, so when I add up everything together, I'll get an input power of 67.028 watt. Okay, so that is the input power, and we need to make sure it lasts for 7 hours. All right, so in terms of the capacity required, it is 67.028 times 7, which will be 469. Let me erase this. 469.196 watt hour. Okay, now from this we can now calculate the load capacity. Okay, so all these are the same formulas we used before in our studio. So we say is 469.196 divided by the operating voltage, all right, of the cells that are already connected in series, so 14.6. So this will give me 32.137 ampere hour, which is 32137 milliampere hour. So this is the amount of current that each that I need to sort of provide, all right, and the depth battery capacity at the depth of discharge is 5000 milliampere hour. All right, so the last step is to take this total amount of load capacity required and divided by 5000. So 32137 divided by 5000 will give me 6.4274. So again, I take the ceiling of it and I will get 7. Okay, that means I need to make sure that the total, I need 7 branches in parallel to provide me with the current, and within each branch I need to have 4 cells in series to provide me with the voltage. Okay, so this is your NP. Okay, number of branches in parallel and number of branches in series. All right, so the option here is option A. Okay, so that is for this question 2. Okay, so that is basically the step. So these are the exact same steps that we have been doing. Like I said, the only thing that you need to be careful about here is whether the subsystems are in series or in parallel. All right, so that's the only difference that you need to factor in. Okay, so let's look at question 3. Okay, so in question 3, you are given this circuit, all right, and we want to obtain V1 as 6 volts and V2 as 2 volts. All right, so in this, we are talking about this thing called a loading effect. Okay, so what is this loading effect? Loading effect is when you connect devices in parallel, you must realize that the overall or the combined resistance of all the branches in parallel can change the voltage across them. Correct? So if I just because, so for example, if this circuit, okay, if I were to just imagine that it is just two resistors, okay, so I have RA and RB, okay, so when I have two resistor values, let's just say it's 5 ohm and 5 ohm, all right, so you know that at this point here is 5 volts, correct? But the moment I connect something else in parallel to RB, okay, it may no longer be having an equivalent resistance of 5 ohm over here. Okay, so if I connect something else here, then the combined resistance may no longer be 5 ohm, which means that the voltage at this point here will change. Correct? So what do we know about resistors in parallel? When I have a very small resistor, let's say 1 ohm, and I connect it to another resistor which is very big, let's say 100 ohm. Okay, even without calculating, I know that the equivalent resistance, all right, will still be approximately 1 ohm. Okay, and I also know another thing, it will be actually lesser than 1 ohm. Right, it will be very close to 1 ohm and it will be slightly lesser than 1 ohm. All right, so that is the rule of parallel resistances. When I connect multiple resistors in parallel together, the combined resistance will always be smaller than the smallest resistance. And if I have two resistors or multiple resistors, it will always lean towards the lower end. Correct? So if I have two resistors, both very extreme, one very small and one very large, the effective resistance will always go towards the very small resistance. Okay, so in that case, if I look here, in order for me to make sure that this voltage here at this point is going to hold on, okay, to its value, all right, regardless of RC and RD, that means the value of RC add with RD must be much greater than RB combined, than the RB alone. All right, so when this happens, when this will make the effective resistance, okay, approximately equals to RB. And when I can do that, that means the voltage at this point here will be more or less the same with or without RC and RD over here. All right, so the only combination where you can see that happening is in combination B over here. Okay, where RC plus RD is much larger than RB. Okay, so 6,000, okay, 6,000 ohm is much bigger than 60 ohm. Okay, which means that when I look at the combined resistance, it's going to be approximately 60. Okay, so when it's approximately 60 here, and this is 40, this voltage here will still be close to 6 volts. So when this voltage is close to 6 volts, then this voltage will also be close to 2 volts. Okay, so that is the understanding you must have. So you must apply the concept or the understanding that when I connect resistors in parallel, we tend to move towards the smallest resistance. Correct? So we must think about what effect that it has and choose the correct resistors. Okay, so this is a bit of a tricky question, correct? Where if you do not apply this thinking correctly, you may get it, you may have some other answer. Correct? Okay, so that is for question 3. Okay, so let's look at question 4. Okay, so in question 4, what is the value of R that will result in a current of 0.1 passing through R. Okay, so in this case, if we never give you the hint, I think many students may not know what to do also, correct? Because you may think, okay, how do I solve this? How do I simplify or so on, correct? But the hint sort of gives you the idea that, okay, I need to apply the Thevenin's equivalent circuit. Okay, so to apply Thevenin's equivalent circuit, that means two things, correct? VTH and RTH. So let's look at the first one, VTH. To find VTH, I must open circuit the load over here. So when I open circuit the load over here, let's see what I get. I got 10 here, okay, 120, 40, and another 120 here. Okay, so this is the open circuit here, and I'm looking at it from here, VTH. Okay, so the VTH is basically the voltage across the 40 ohm resistor, correct? So you can see that when the current comes out here, it will split into 120 and split into this 120, and then it join back and go into the 40. Alright, so effectively this 120 is parallel to this 120. Okay, so you can redraw the circuit again one more time. So this 120 is 60 and this is 40. So the voltage you're interested in is this point over here, and you can just apply your voltage divider rule. Okay, so since this is 10 volts, okay, you automatically know that this is 4 volts. Alright, so your VTH is 4 volts. Alright, so the next step is RTH. So RTH, we short circuit this point here. Okay, and then you have 120, another 120, okay, 40, and here. Alright, and then the sort of technique that I told you is, imagine that I put a voltage source here, and how will the current flow? So when the current comes in, so this point and this point, as you can see, is a short circuit here. That means they are both the same point, right? This point here and this point here are the same. So you can sort of redraw it, okay, where this imaginary supply is connecting to a point where you have 120, another 120, and then another 40. Okay, and all of them coming back over here. All right, so that is basically how the current will flow. It will come out here. So some will go through this 120, some will go through this 120, some will go through this 40. Okay, so the effective RTH here is 120 parallel to 120 parallel to 40. All right, which is 24 ohms. Okay, so once you have VTH and RTH, you can redraw your circuit here. So you have 4 volts. Okay, you have 24 ohm. Okay, and you want to find a value of R that would make the current 0.1. So you just apply Ohm's law. Alright, so I equals to 0.1, which is 4 over R plus 24. Correct, and from there you can get your R to be equals to 16 ohms. Okay, so that is for this question 4 over here. Okay, let's go on to question 5. Okay, so in question 5, we're asking about maximum power that can be utilized by load R. Alright, so the maximum power, whenever you see the word maximum power, you automatically, the thing that should trigger in your mind is, again, Thevenin equivalent circuit. Alright, because we know that maximum power is delivered to the load when the source resistance is equal to the load resistance. Alright, so the source resistance you obtain by finding the Thevenin's equivalent. Alright, so you have the Thevenin's voltage, Thevenin's equivalent resistance, and when the same Thevenin equivalent resistance is applied to the load, that is when you have the maximum power transfer happening. Okay, so this maximum power is a keyword to tell you that we have to use the Thevenin's approach, all right, to solve the circuit. Okay, so if you look at this circuit, all right, when I open circuit this, okay, so if this is now open circuit, all right, what do you see? Okay, so to analyze this circuit, we must understand the way it is connected. You can see that these 3 points are actually shorted together, all right, without any component in between. So this actually acts like a common point that separates out this circuit from the rest of the circuit here. Okay, because when you have these 3 points as common, all right, you can treat this part of the circuit as separate, all right, and this part of the circuit as separate. Okay, again, the way you can sort of see this is, if I have the positive of the one source connected to the negative of another source directly without any component in between, then that acts like a common ground that I can separate out 2 circuits. All right, so effectively you can imagine that the only circuit you need to focus on is actually this part over here. Okay, so what you have here is just 10 volts, okay, 10 ohm, 20, 10. Okay, so I'm open circuit the load over here. Okay, and this is the VTH I'm looking at. Okay, so what is the VTH? The VTH is the voltage seen over here. All right, and since this is open circuit, it is the same voltage seen from this point over here as well. Okay, because this is open circuit. Right, so open circuit means there's no current flowing here, so the voltage at this point with reference to ground is the same as this point with reference to ground. Okay, and since the only path for current to flow is through this 10 ohm and through this 10 ohm, the voltage here is basically half of this, correct? Because 10 and 10. So this is 5 volts. Okay, so that is how you get the VTH over here, which is 5 volts. Yeah, so in this case, because of the way that you have a common point here where the plus is connected to the negative of this, we can treat them as 2 separate circuits. Alright, so that is why we only need to focus on this. Okay, and once I find VTH, the next step is RTH. Okay, so the plus connected to negative is this plus, that means the positive of the supply here connected to the negative of another supply here. That means you consider that this can be treated like a common point where the 2 circuits can be separated. Okay, it's like a common, you can think of it like a common ground where you separate out circuits, all right, and you can analyze them separately. Okay, so that is how you can think of it. Okay, when they share a common ground, all right, so the common ground could be points like this where you have sources connected together without any other component in between. Yeah, so there is no resistance in between, which makes it a common point. All right, if there's a resistance, then the voltage at the point might change. All right, so it may not be. So if there's a resistance here or resistance here, then it's different. All right, it's not a common point anymore. Okay, so this has to be a common point. Then you can treat it as a common ground, and then separate out as different circuits. Okay, for the, let me go on first. Okay, like I said, I will finish up, and in the end, if you still have questions, I will still stay around to answer all your questions. Okay, for the RTH part, okay, what we need to do is we need to remove the source. Okay, so if I were to redraw it, okay, so the 10 volts is now short circuited. So I have 20, I have 10, and I have 10 over here. All right, so if I imagine that I put a supply over here, basically what will happen is you will go through, the current will go through here, and at this point of time, it will split into this branch and split into this branch. Okay, so since it's going through the 20 ohm first, that is considered series. Then I split into 10 and 10, so it is 10 parallel 10. Okay, so the total resistance will be 25. Okay, so the Thevenin's equivalent circuit can be redrawn as this: 5 volts, 25 ohm, and this is your R. Okay, so your R here. So what is the maximum power that can be utilized by the load R? So the maximum power is only when the load resistance is the same as the source resistance. So this is also 25. All right, then you can use your any of the formula I square R, V square over R, whatever, to find the power delivered to the load. Okay, so if I were to use V square over R, this voltage would be 2.5 volts. So 2.5 square over 25, I'll get 0.25 watt. Yeah. Okay, so if you continue drawing a straight line down from R between 30 ohms and 10 volts. Let me see where from R. Okay, so if you're saying that you draw a straight line like this, then this is, I mean, this is not a correct circuit in the first place because you're short circuiting the 10 volts. Okay, but if you were to put another resistor here, okay, it will still be considered as two separate circuits because these 3 points are all connected together still. Okay, so effectively this is considered like one separate loop. Okay, and this circuit will still be considered separate. Okay, because of the way it is connected over here. Okay, so here you cannot have a straight line because if you have a straight wire here, you will short circuit this 10 volt supply here. All right, but if you put a resistor here, it's still fine. Okay, let me see. Okay, how do you know which end is positive or negative? All right, so in this case, you can like what we always do. If you are going to find, okay, for Thevenin's equivalent, basically you are just trying to find based on the voltage, okay, with reference to the ground in the circuit. All right, so what I'm interested in, I'm looking at VTH over here. All right, and to me, like what we are doing here is we are trying to see what is the voltage at this point. Okay, and the voltage at this point, this is connected to the negative over here. So we say that this is the ground reference. All right, so with reference to this point here is positive. Okay, so we calculate as 5 volts. So that is why we draw the source as this way. Okay, if you were to have drawn this supply the other way around, all right, that means if you had drawn this supply this way, okay, in the circuit, for example, okay, let's just look at this circuit alone, then the current flow would have been this way. All right, so the VTH that you draw, this would have been the ground. Right, this would have been the ground, this would have been the 5 volts. So it is the same 5 volts, only thing you would have drawn the supply the other way. So the positive or negative, it depends on the current flow, all right, through the load. Okay, so that is how you define. So when you first take VTH, we are trying to find the voltage, correct, and we always use the reference ground as the starting point. So in this case, since the ground here from the source that we already have is at the bottom. So we put this as the ground. So we take it that this is negative and this is positive. Okay, but if let's say in the end the answer is that you get for VTH is a negative answer, then that means you just have to draw it the other way around. All right, that's what it means. Okay, if that was the case. Okay, let me go on to the next question here. Okay, so here we have a current of 8 ampere flowing through a resistor network. Okay, find the voltage difference. Okay, so to find the voltage, okay, what I need to do is I first need to know the combined resistance. All right, so if I look at this, okay, you can see that I have 8 ampere here, and I have 3 branches. So one is 12 ohm, so this one is 8 ohm, and this one is also 8 ohm. All right, so it's effectively 8 parallel with 12 parallel with 8. Okay, and that means I will get a total current. Okay, 8 parallel with 12 parallel with 8 is 3 ohms. Okay, it's 3 ohms. So the total effective resistance here is 3 ohms and 8 ampere is going in. All right, so the voltage drop across here, the total voltage drop is 8 times 3, which is 24 volts. All right, since all these 3 branches are parallel, the 24 volts appears as the same across all 3 branches. Okay, now the next thing is the current. Correct, the current. So since I know 24 volts is the voltage difference across all these 3 points, I can calculate the current. All right, so 24 divided by 12 over here, I'll get 2 ampere. So here I get 2 ampere. Okay, 24 divided by 8, I get 3 ampere here, and here I get 3 ampere. Correct, so this part we know. All right, so if I draw it here, I got 2 ampere here. All right, I got another 3 ampere here, another 3 ampere here. Okay, so now what is going to happen? When 3 ampere goes through this 2 ohm, what happens? The voltage drop across this 2 ohm resistor is 6 volts. All right, when the 3 amp go through this 4 ohm resistor, the voltage drop across here will be 12 volts. Okay, so what is the voltage remaining at this point? All right, so since the total branch is 12 volt, 24 volts. So if 6 volts drop here, left here is 18 volts. If 12 volt drop here, left here is 12 volts. All right, so the difference between X and Y is 6 volts. All right, so the answer here is B, 6 volts. Okay, so it's just like you draw it a straight line, correct? Okay, so if I tell you that I have 3 ampere going in, and I have 2 ohm resistor here, and I have a 6 ohm resistor here. So the voltage drop across here is going to be 6 volts. All right, so if the total voltage across both these components is going to be 24 volts, so what is remaining at this point, okay, across the 6 ohm resistor would be 18 volts. Okay, so that is how you get the voltage at X and Y. Okay, so it is not the voltage drop across the first resistor. It is the voltage at the starting here, subtract the voltage drop across the first resistor, and what is remaining. Okay, so what is remaining here is 18 volts. What is remaining here is 12 volts. Okay, and that's how you get the 6 volts as the difference. Okay, so let me go on the next question. So here they ask us to find VA. So the voltage here VA is this with Okay, so here is where you can apply your node analysis. All right, so you can take it that all the currents flowing in, okay, into this point here. So this branch, this first branch here would be 15 minus VA over 2, plus this branch will be 10 minus VA over 1 plus 0 minus VA over 5 equals to 0. Okay, and then you solve for VA, you should be able to get 10.3 volts. Okay, so this one is just simple node analysis. Okay, something we have done before in our earlier sessions. Okay, so the next question, question 8, is related to this. So we know that the point VA is 10.3 volts. So this point is 10.3 volts. All right, so in this case, if it is 10.3 volts here, all right, we can see that this is 10 volts. So the current is now going to flow in this direction. Correct? So the current will be the voltage difference between the resistor 10.3 minus 10 divided by 1, which will be 0.3 ampere. Okay, and so the power is VI, correct? So VI is 10 volts, which is the source, multiplied by 0.3 ampere, which will be 3 watt. Okay, so this device is going to be consuming power of about 3 watts. Okay, so this is something we saw in our handouts as well. If the current is flowing out, all right, then we say it is supplying power. It is going into the device, it is consuming power. All right, so consuming power, okay, is basically the whole concept of, for example, when you charge your batteries, correct, you are actually sending current into the battery, correct, to charge it. All right, so that is basically the idea of how you can consume power. Okay, so let's go on to the next question over here. Okay, so for this question, we asked to find the voltage of V1 with respect to ground. Okay, so here is, you must again use node analysis, correct? So how do you do this node analysis? If you, of course, during the midterm, okay, or you're trying on your own, there's always a chance you may try something and then it doesn't work. That means you cannot come up with a proper equation, or something doesn't add up because you do not know how to define a particular node. Okay, then you know that most likely that part is wrong. All right, so the whole idea of node analysis is I must be able to define some voltages of the different nodes with respect to ground or with respect to some other voltage that I'm trying to find. And then using that, I can come up with some equation. So that's the whole idea of node analysis. All right, because if you maybe have a different thinking and you try some other approach, all right, if let's say you're not able to come up with a proper equation, all right, then you know that that approach was wrong. Step back and try to take a different approach. All right, so over here, like I said, here we have one node. Okay, and the only other node left is this node. Okay, so how do I define this node with respect to this? So here I have a 12 volt supply. So if this is V1, this node is always going to be V1 plus 12. Correct, so that part is what we know. So we are able to clearly define the voltage at this point with respect to V1. Okay, now the next step is coming up with equations. So to come up with equations, you can either come up with equations that help you to form an expression that can effectively be solved. Okay, so that's the whole idea. So you can think of how you want to do it. All right, one way is you can define this section here as a supernode. That means you take all the current flowing in to this supernode as 0. Alright, we add up to 0. So if I take that approach, then I can say that V1 plus 12, alright, minus 10, okay, divided by 1, that is this current over here, plus V1 minus 0 divided by 4, which is this current over here. Both of them add up to 0 with all the current flowing in. Okay, and with this you can solve for V1, okay, and you get negative 1.6 volts. Okay, so the voltage here is negative 1.6 volts, all right, with respect to ground. Okay, so the ground is basically we treat it as a reference point in a circuit. Normally, okay, when you connect a power supply, you connect the positive and negative, correct? And normally what we do is we will take one of the negative or maybe all the negative to be considered as a ground. That means the common reference point for this circuit. When you say current flowing into the ground, generally what we mean is it sort of goes back into the negative of the supply. All right, so we don't say the current goes into the ground that way. The ground is just treated as a reference point for us to do the calculation. Okay, grounding in essence, like I said, we treat it more as a negative of the supply that current flows back into, okay, in a normal closed loop circuit. Yeah, so this ground is not the same as your AC ground. All right, in the AC supply, when you have the ground, that ground is really ground. All right, because that means when your appliance gets damaged, all right, there's a short circuit in your water heater or something like that, okay, then that spike in the current would be channeled to the ground. All right, that means the electrical cable in your building will transfer that current to the ground. All right, so that is the protection mechanism in the AC supply. Correct. In a DC supply context, the ground is generally the negative. Okay, how do we determine current direction? We do not know the current direction. All right, so we are just taking some reference point and then calculating from there. All right, so from there we will know the current direction. So for example here, we can see that V1 is negative 1.6 volts, correct? Right, respect the ground. That means what? That means current flows from the higher voltage to the lower voltage, correct? So actually the higher voltage is this ground, correct? That means now that you know V1, we can now say that the current is actually flowing in the opposite direction here in this branch. Okay, wait, let me look at the charts. Plus. Can we use V1 plus 12 to do the analysis? Can we do this with a constant supernode? Okay, if you want to do this without supernode, all right, it's possible. Okay, provided I did not try it yet, but if you try it, if you can come up with proper equations that can define a particular node, then it is fine. All right, so you see the main idea is you want to come up with a set of equations that define current flow to a node. All right, and if your equations are correct, you should still be able to solve for the unknown voltages. All right, so the supernode is not say a compulsory thing you must do every time. Okay, without the supernode, if you can come up with the proper set of equations that can help you to solve the unknown voltages that you're looking for, is also fine. Okay. Okay, so you can use techniques that you have learned, all right, KVL, KCL, node analysis, Thevenin's, whatever, all right, everything you can use, all right. But when you have this kind of circuits with multiple voltage sources and you are trying to find one voltage with respect to another voltage, okay, in most cases, using the node analysis is one of the better options. All right, but you are free to try anything else. Okay, so in the same branch, is current flow going to be the same or is it going to be different? All right, so if you look at this branch, okay, so this is considered one branch. All right, so in one branch of a circuit, current will flow in only one direction. Okay, that means if here I say the current is flowing this way, all right, then that means over here is going this way. All right, but when we are doing the analysis, it is okay to assume whatever you want to assume. Okay, so that is why to make our calculation easy, we always assume all the current go in, all the current go out. Correct? Okay, so if you think about it, okay, if now that I calculate V1 is negative 1.6, okay, okay, so the negative is all about how you define your directions. All right, so like I said, we initially assign a direction this way to help us come up with the equations, correct? Now, after we solve this, we know V1 is negative 1.64, so the actual current is this direction. Now, applying this over here, we get that this point here is going to be 12 minus 1.6, correct? It should be 10.4 volts, correct? Okay, which means that the current 10.4 volts here, this 10 volts, means the current is going in this direction. So it all adds up now, correct? That means from this point to this point, current is going in the clockwise direction. All right. So our initial assumptions of the current direction is whatever. Okay, that is to come up with the equation. After we come up, all right, we know that okay, this is the voltage, so we know the current flow. Okay, whether I want to call this positive current or negative current now depends on my direction, knowing how the current is flowing. So okay, so let's assume. Okay, let's assume that I say this is 1 ampere flowing in this branch. Okay, just assume this. Now that I know that this is the direction, if I draw my current arrow this way, I call this 1 ampere. If I draw my current direction this way in this branch, then I must call this negative 1 ampere. Correct? Because now I know that the current is actually going this way. Okay, so the positive or the negative convention is whether you know or you don't know yet. When you do not know, correct, when you're coming out with your equations, we assume something and then we calculate. And after we calculate, then we can assign. When you are now going to assign, all right, it's a matter of whether you want to stick with the original direction that you gave or you want to change the direction and call it something new. So if I want to stick to the original direction that I gave, correct, that means if I originally call this I1 and I originally call this I2, All right, I can stick to it and say this I1 is 1 ampere and I2 is equals to negative 1 ampere. But if now that I know, I can say that, okay, I will call this current as I3. And I3 is 1 ampere because this is the actual direction of the current. Okay, so you can stick with the original assumption of your directions, and then your plus and minus will then be following that original assumption. Or you can make a new assignment, correct, to reflect what you have just learned. Okay, what is the actual current flow now? All right, so it is just a convention based on whether you make the initial assumption or you make the final conclusion with the values that you've already calculated. Okay, so that is how you sort of get your plus and minus. All right, so to put this in perspective, okay, so let's assume that the question, okay, let's assume that the question is the same circuit. Okay, so I don't want to spend too much time on the same question now. Okay, other questions beyond I will answer later. Okay, if not, we will be stuck here. All right, like I said, the convention we will follow is either before you know or after you know. All right, and whether the question itself has assigned the arrow for you. All right, so let me just give you one more thing before we end this question. Okay, so let's say the same question comes out. Okay, I don't know if it's coming out. I haven't looked at the questions yet. Okay, but let's assume a similar question comes out. All right, but instead of asking you what is the voltage, they draw for you this arrow here. Okay, they draw this arrow and they tell you this is I. Okay, this green arrow here is I, and they ask you to find I. Okay, and okay, let's assume that after you calculate everything, the answer that you get for this branch here is 1 ampere. All right, and over here you know that this is negative 1.6 volts. So you know that right now the current is flowing in this direction. Okay, so if the current is now flowing in this direction, what does it mean? That means this I has to be a negative value because now you know already. Correct, you know already. So since you know that the current is negative, so the option that you choose must be a negative current. All right, because you are now answering based on the question which has already given you the arrow. Okay, so when the arrow is already drawn for you, okay, and then when you get the final value, the answer you give must reflect the arrow that has already been given to you. Okay, so now I know that the current is actually flowing in this left direction, but the arrow given in the question is going to the right. That means the answer should be a negative current. That should be a negative current. So that is how you look at the convention of positive or negative. Okay, so let me go on first to question 10. Okay, so this is on inductor. So in this circuit, the switch has been open for a long time, and the current measured by the ammeter is 1 ampere before time t equals to 0. Okay, so you are reading 1 ampere here. At time t equals 0, the switch is closed. Okay, what will be the voltage? Okay, so the first thing we understand is if it has been open for a long time, that means we have current flowing in this part of the circuit for a very long time. Okay, which means that your inductor, okay, has achieved steady state. And inductor steady state is equivalent to short circuit. Okay, so that is the first understanding you must have. So if the inductor is already at short circuit, that means this is equivalent to having a short circuit line. All right, so the only voltage drop that this, or the only thing that this circuit will see is this 12 ohm resistor. So the full entire voltage will come across here. So this and this are short circuit, which is going to be 0 volts, correct? Because any short circuit branch is 0 volts on both sides. Okay, because there is no voltage drop across a short circuit. Okay, so what will be the voltage V2? So this V2 is effectively not seen at all, correct? Because this is open circuit. So the V2 is this voltage over here. Okay, so this is V2. Okay. Okay, so this is your V2 over here. So your V2 is the same as your V2 over here, or this point over here, which is connected to the negative. It means 0 volts. All right, so that is how you get the answer for this. Okay, so in this circuit 11, you are told that the switch was initially open for a long time. All right, and at time t equals 0, the switch is closed. What is the inductor's voltage at time t equals 0.2 seconds? All right, so again, the same thing. If the switch is open for a long time, that means this behave like a short circuit. All right, so if this behave like a short circuit, current is only now flowing in this branch, all right, through this part here, and this is open, correct? So the current, okay, through the inductor at 0 minus before the switch is closed is 10 over 10, all right, which is 1 ampere. All right, and this is the same current at 0 plus, correct, because we know that current through the inductor cannot change instantaneously. So when I first close the switch, it will also be 1 ampere. Okay, so when I close the switch, all right, what I will see is I will have an inductor and 2 resistors. You have to remember that in order to apply the standard formula that we have, it must be RL in series. All right, which means that this 10 ohm and 10 ohm must effectively be redrawn as a single supply. A single resistance. So this is equivalent to 5 ohm. Because only when you have RL in series, you can apply the standard formula. So what is the standard formula? You should basically know it. IL0 e to the power minus t over tau plus IL infinity 1 minus e to the minus t over tau. So in this case, your tau is L by R. Okay, so that part you can get based on this L and this R. Okay, now what is IL0? So IL0 is the initial current going through the circuit, and that is 1 ampere. So this is 1 ampere. Okay, what is IL infinity? So again, IL infinity means if I let this circuit run for a long time, all right, when it's going on for a long time, what will happen? That means it comes back to this inductor behaving like a short circuit, correct? And if this is a short circuit, that means this is just a normal wire. So the only thing that you have in a circuit is this 10 ohm and 10 ohm in parallel, which is the 5 ohm. So the IL infinity will be 10 volt divided by 5 ohm, which is 2 ampere. Okay, and your tau is L by R, which is 1 divided by 5, which is 0.2. Okay, so you put in all of this inside your expression. Okay, you will get your current. Okay, at time t equals to 0.2, you substitute t is 0.2 inside. What you get, your current should be 1.632 ampere. Okay, and your voltage, okay, is basically your supply voltage subtract the current 1.632 multiply by the voltage seen across the 2 resistors here. So you get 1.84 volts. Okay, so you can look at the voltage seen by the voltage drop across the equivalent resistance over here, and whatever is left is the voltage across the inductance. Okay, so your answer here would be B. Okay, so this is the last question. There were, of course, two questions that is not here because they were AC questions. Okay, so let me just answer this question. Okay, so you can see that you cannot directly apply Ohm's law for the inductor or the capacitor. Okay, because Ohm's law is V IR, correct? So we don't have the we can't apply that here. We can apply to resistor. So that is why we take the supply voltage minus the voltage drop across the resistors. Okay, then we find the voltage remaining, and that is the voltage across the inductor over here. Okay, so let me go on to the last question here. So in this last question, let's look at this. So switch 1 is closed and switch 2 was open for a long time. All right. So let's look at what is going to happen. So at time t equals to 0 minus. Okay, that means it's been just before you do anything to the switches. So if this switch is closed and this switch is open, so this part of the circuit is not seen. So this 50 ohm is not seen in the circuit because no current is flowing here. So all you have is this resistor, this resistor, this resistor, and this capacitor here. And once you allow the capacitor current flow inside the capacitor to go for a long time, it will basically become fully charged. Correct? So a capacitor, okay, in steady state means it behaves as a open circuit. Okay, so the equivalent voltage, okay, that is here, the equivalent voltage that is here is the voltage that you see, okay, from this part of the circuit if I redraw it this way. Okay, so nothing is going to go in through the 30 ohm because this part here is now considered open circuit because the capacitor is open circuit in steady state. Okay, so if the capacitor is open circuit in steady state, the only path for the current to flow is through here. Okay, so the voltage seen by the capacitor is basically 10 by 30 times 30, which is 10 volts. All right, so this is the voltage across the capacitor at t equals to 0 minus. Okay, once at t equals 0 plus, when I open this and I close this, all right, then what happens? What you see is you see the capacitor connected to 50 ohm and 50 ohm. Okay, this is a capacitor. All right, and the voltage across the capacitor will still initially be 10 volts, correct? Because VC 0 plus will be the same as VC 0 minus. So initially, VC 0 plus will still be 10 volts. All right, and then what will happen? The capacitor will start to discharge through these two resistors here. Again, in order for me to use a standard equation, it must be a single resistor and a single capacitor in series. So this is combined together. Okay, so 2 in parallel is equivalent to 25 ohm. Okay, so your tau is RC, all right. So that will be 8 milli multiplied by 25 should be 0.2 second. Okay, and your expression is the standard expression Vc0 e to the power of minus t by tau plus Vc infinity 1 minus e to the minus t over tau. Okay, so what is Vc0? Vc0 is 10. Okay, e to the power of minus 1. What is Vc infinity? Vc infinity means if I let it discharge for a long time, correct? So we know if I let it discharge for a long time, effectively it will go to 0. So I don't need to worry about this. Okay, so the voltage I'll get is 3.68 volt. Okay, so what is the current? Okay, so the current, again, I must use Ohm's law for the resistor. So 3.68 volt is the voltage that is seen here. Okay, after at 0.2 seconds. So the current is 3.68 divided by 25, which is 0.147 ampere. Okay, so that basically wraps up the first paper. Okay, so what are any questions you all have regarding what we went through? You can, any other questions?
Oh, Professor?
Yeah.
Yeah, for question 9, I still don't, for question 9, when we do the supernode at the 10 volt voltage source, because the thing is, the current on top and the current below are in opposite direction. Because if we don't put a sign convention and we say that, that means we're implying that the current I1 at the top and the current I1 also at the bottom, both of them are entering the positive and negative side of the positive and negative terminal of the 10 volt. So isn't that wrong?
Okay, so it comes back to what I said just now. When you want to come up with the node equations, okay, we assume everything. So it is the same idea. When we look at node analysis, okay, let's say if I go back to this, correct? Is it possible that all three currents go into this node? Cannot be, correct? There has to be one of the branches current has to be going out somewhere, correct? So it's the same thing. So we do not know, and then we assume. We just come up with an assumption that all the current are going in. All right. So that assumption, we know that one of it, at least one of it is wrong. Okay, we know that for sure. But we can still make the assumption because after we calculate the value, then we will be able to know whether which assumption was right, which assumption was wrong. So if I look at this example, it's the same thing. I assume that all currents going in, even though I know it is wrong. All right. But after I calculate VA, I know that this is 10.3 volt, which means that this direction was correct.
I understand this part because all these three are all different currents. So like even if one side is wrong, then we can flip all instances of like what of maybe current I1 is wrong. So if you flip at the end, it'll be all instances of current I1 is negative. But for this case, it's one instance is correct and one instance is wrong.
Okay, so
both is correct. That's the thing.
Okay, so it is wrong. Okay, it is wrong if you label the two currents with the same name. Okay, that means if I call this I1, all right, and I call this also I1. Okay, so maybe I too much there. Okay, so I just draw this part here. Okay, so if I label this as I1, all right, and if I label this as also I1, then it is wrong. Okay, then if I use I1 in my equation, okay, if I use I1 to form some equation, all right, with this labeling convention, then it is wrong. All right, because like what you said, you are trying to say both of these currents going in opposite direction to the same place, which is wrong. All right, but if I label this as I1, I label this as I2, then I form my equations based on I1, I2 is perfectly fine. Because in the end, I can just say that I2 is equals to negative I1. All right.
But in this case, won't they cancel out at the end?
No, they won't cancel out because they are considered two separate currents when you label them differently.
Yes, because it's if you label it like this, is I1 plus I2 equals to 0. Then I2 is equals to negative I1. So
Correct.
the
Correct.
whole
That
thing
means the current is
zero.
actually going in this direction. Correct. It comes back to the same thing over here. It's the same idea over here. We assume everything go in is 0. Correct. It's the same concept here. That means you assume two currents. Okay, as long as you label them different. In our case, we're not using current labels. We are coming up with current equation based on voltage label. So as long as you assume a particular convention and you derive all your equations based on one convention, then it is fine, because the final answer will then be able to tell you whether that assumption was right or wrong.
Oh, okay. I understand already. Thank you, Professor.
Okay. Okay, so okay, question 10. Okay, why is this 0 volts? Okay, basically because as we saw, when inductor in steady state behave like a short circuit. So when it's a short circuit, okay, any component that is short circuit. So imagine I draw a circuit here, 10 volts. Okay, this is one resistor R1 and take another resistor R2. All right, and let's assume that originally there's a resistor here, R3. All right, if now I take out this resistor, all right, and I create a short circuit here, now what happened? That means this voltage is the same as this voltage, which is actually connected back to the ground. Okay, that means it's 0 volts. Okay, the moment I have a short circuit path connected back to ground is 0 volts. But it's not only to ground. Any short circuit point will also be considered as a 0 volt, because you have a voltage drop across a component, okay, when you have current, okay, so how to put it, okay. So the voltage difference between two places can only be seen, okay, if there is some sort of component there, correct, either a resistor or a capacitor or inductor. So even if I take, for example, this point here, okay, this point here, and I take this point here, okay, what is the voltage here? The voltage here and the voltage here will be the same, correct? The voltage here and the voltage here will be the same. So if I try to use a voltmeter to measure the voltage across these 2 points, okay, across these 2 points, what will I get? I will get 0 volts. All right. If I take this with respect to ground, that is different. Correct? Because then I'm taking this entire branch, which is the voltage across R2. But if I just try to take a voltage across any 2 points when it's just a short circuit wire, the voltage at both these points will be the same. Correct? So the voltage difference will be considered 0 volts. All right, because the voltage is the same at both these points. So the same thing applies here. So the voltage at this point here and the voltage at this point here are exactly the same because the short circuit. So as long as you have a short circuit, the voltage at both these points is the same. So the voltage difference is considered to be 0. Yeah, so the current is still flowing because now this is like a short circuit. Okay, so if this is a short circuit, okay, so it behaves just like a normal series circuit only. That's all the circuit sees. Okay, it doesn't see the inductor anymore because it behaves as a short circuit.
Prof, can I ask something? So in this question, if you say you put a switch between 12 ohms and the emitter and then you open it, the answer will be -6 or 6.
Which one? Sorry again. If I put a switch here.
Yes, and then you open it. So then the answer will be -6, right?
The answer would be when you first open the switch, is it?
Yes, time t equals to 0 plus.
At time equals 0 plus, the current through here would still be 12, 1 ampere. So 1, yeah, so it will be considered negative 6 volts. Yeah, correct.
Okay, thank you.
Okay, so let's go for a short break. Now it's 3:25. Okay, so let's have a short 10 minutes break. At 3:35, I'll come back here. Okay, and then we will go through the AY1819 paper. Okay, so about 10 minutes time, I'll see you all back here. Let's carry on with the AY1819 paper. Okay, so let's review these questions. Okay, so question 1, an appliance consists of 3 subsystems working in parallel. All right, with the following power efficiencies, the minimum input power required by appliance if each subsystem output power is 600 watt. All right, so as you can see, it's a bit similar. All right, so the questions are a bit similar. So here we have 3 subsystems, 96%, 83%, and 91%. All right, so each of these subsystems output power is 600 watt. All right, so the input power requirements for each of them would be, you divide, correct, by 96%. This is 600 divided by 83%, and 600 divided by 91%, and then you add them up together. That is your power in, and that would give you 2007.2 watt. So you round up to 2008. Okay, so the minimum input power required, all right, to sustain this system is 2008. All right, so the answer here is B. Okay, question 2. What is the discharge current of a 12,000 milliwatt hour battery operating at 3.6 volt and 0.2 coulombs? All right, so for this one, basically the same thing as before. So if I'm operating, or the battery power rating is this 12,600 milliwatt hour, all right, so that is equivalent to 12.6 watt hour. All right, so in terms of the current is 12.6 divided by 3.6, which will give me 3.5 ampere hour. All right, so 3.5 ampere is the amount of current that would have been discharged if I operate in 1C. All right, so since I'm operating in 0.2C, it is 0.2 times 3.5, which will be giving me 0.7 ampere. Okay, we did this. All right, so that is how you get the answer for this. Okay, so most of the questions on the battery and this efficiency and all are quite standard. Okay, so this is also quite standard. All right, exactly the same. All right, exactly the same. The only thing is this. All right, they are operating in series. So this is the thing you need to be careful about, like I mentioned earlier. All right, so in terms of power efficiency, the input power would be the output power divided by all the efficiencies multiplied. Okay, so this formula is shown inside your handout. Okay, so the input power will be 161.5 watt. All right, previously was individually you did, okay, when they are in parallel. All right, then you look at the output requirement of each subsystem. All right, so just read the question carefully. Of course, they can also change the variation. They can say subsystem 1 output power 80, subsystem 2 output power 70, and so on, and each of them is parallel. Okay, or we could have a variation of 2 subsystems in series, 2 subsystems in parallel, Alright, so these are some of the variations. Ultimately, we just need to make sure that we calculate the input power correctly, depending on which subsystems are in series or in parallel, or it's a mix of both. Alright. So of course, the first step, I actually jump to the second step. The first step is the voltage. Alright. So since I want the instantaneous C rate of 2C gives us 3.6 volt, and I want required operating voltage of 17. So 17 divided by 3.6 would have given me 4.72. So you take the ceiling of that, which will be 5 volts. Okay, so that is your NS, a number of cells in series. Five cells in series. Okay, so you have the power. So in terms of the capacity, load energy, the load energy, okay, what you get is 161.5 multiplied by the number of hours that you need to operate, and that is here 6 hours. So that will give you 969 watt hour. So the capacity would be 969 divided by 80. All right. So with that, okay, we can say that the requirement is 53.8 ampere hour. Okay, and each in the depth of discharge for a single battery capacity, the current is 6,000 milliampere, which is 6 ampere. So 53.8 divided by 6, I will get 8.97. So you take the ceiling of that, you'll get 9. So that is your cells in parallel. Okay, so 5 and 9, answer is A over here. Okay, so all these are quite standard, right, from what we have been doing all the while. Okay, so let's look at question 4. So in question 4, I ask you to find the voltage difference between A and B. Okay, so to find the voltage difference between A and B, we first need to sort of simplify the circuit down, okay, to find this actual voltage. So this A is this point here, or this line, B is this line over here, correct? So basically you can see that when the current comes out, what will happen, it will split into this and this, correct? So 120 are parallel, and this line sort of combines them together and then splits them up again. All right, so you can sort of redraw it in a way that maybe it looks a bit more easier to understand. Okay, so you can actually draw it something like this. So you can see it's 120, 120, 100, and 150. Okay, so these two combined together will give me 60. Okay, these two parallel together would give me 60 also. Okay, which means that the voltage at this point here is 5 volts. Okay, so that's the answer over here, 5 volts. Okay, so the main thing is, as long as you can see that these two are parallel and these two are parallel, all right, then you will be able to get the correct answer here. Okay, so this question, again, something similar we saw just now. Okay, so the first thing is you combine them to, okay, in this case, you don't necessarily need to combine and find the total resistance because you know the current. Okay, so one way is you just combine the two branches, the series. So this is 8 ohm and this is 16 ohm. So 3 ampere coming in here. Okay, when you only have 2 branches, all right, you can straight away apply the current divider rule. In the previous paper, we have 3 branches. Okay, so for 3 branches, you cannot directly apply current divider rule. Okay, you still need to combine and then find the voltage and so on. For only 2 branches, it's easier because you can straight away apply current divider rule. So to find the current through this, I take the opposite resistance. So I take 16 divided by 16 plus 8, which is 24, multiplied by the incoming current 3, and that will give me 2 ampere. So 2 ampere comes in means automatically I know 1 ampere comes in here. So 2 ampere comes here and 1 ampere comes here. So if 2 ampere comes over here, then so you can see that the total voltage drop here is 16 volts, all right, plus minus 16 volts. All right, so if 2 ampere comes in here, 3 times 2 will be 6 volt drop here. So total initially at this point is 16 volts. 6 volt drop here, I get 10 volts. 1 ampere go through here. Okay, 12 ohms here. So sorry, 1 ampere goes in here, 12 ohms. So I got a 12 volt drop here. So 16 minus 12, I get 4 volts. All right, so the total difference between X and Y is 10 minus 4, which is 6. Okay, so very similar to earlier question, you just need to find the current through that particular branch. All right, and then you can use find the voltage drop across each of that initial resistor, and then you know what is remaining at the 2 points X and Y. Okay, so that is basically what you have to do. Okay, this question 6. So in this question 6, what you have? You have a resistor network. Okay, what is the equivalent resistance? Okay, so what do you see here? You see it is a bit complicated, correct? And you see that the current that comes in through here will split into this. So you can treat it as, okay, so if you were to try to redraw it, okay, you can think of it as, first I have these 3 resistors here. Okay, then go through another 2 resistors and then go through another resistor, correct? And over here I have another resistor here. Okay, and this is 10 ohm. So what did we sort of understand from the earlier question and the other paper? That when I have when I have parallel branches, the final resistance will always be smaller than the smallest resistance in any of the branches. Correct? So since I have 10 over here, I know that the final resistance, okay, the total resistance here has to be lesser than 10. Okay, so I don't need to calculate anything. I can straight away say this answer. Okay, because when I have resistors in parallel, the final resistance will always be smaller than the smallest resistance. So since I have 10, the total resistance is always going to be lesser than 10. Okay, and the only option here which is lesser than 10 is this. All right, so if you see this, you can get the answer very quickly, correct, without calculating anything. All right, so that is basically what this question is trying to test you on. Okay, so for this question, question 7 is Thevenin's equivalent. So what is the Thevenin's resistance? Okay, so here they are going to ask you to find the resistance. Okay, so for the resistance, basically we short circuit this, correct? So if I short circuit this, okay, and like what I told you, you imagine you put a source here. So let me draw it both ways, okay? Then you can see if I draw it this way or I draw it this way, okay, it makes no difference. Right? So effectively, what do you see? You see that when the current comes out, okay, so if let's say I look at it from this left hand side circuit, if the current comes out here, what will happen? It will split into this branch and it will split into this branch. Alright, when it split into this branch, there is a short circuit branch here. Alright, so some current will flow here, but effectively, when the current leaves the positive, it has to come back into the negative. So it has to still again split into 3 and 4. Right, so even though the current comes here at this point of time, at this point here, yes, you may have some current flowing in this branch, all right, but effectively to get the closed circuit, it has to come back in through the negative terminal here, all right, which means that I will split into 1 and 2, combine together, and then split into 3 and 4. if I look at it from the other perspective, okay, so if I try to draw the imaginary voltage source the other way, it's still the same thing. I will split into 3 and 4. When I come here, and I have a short circuit, but even if I go through the short circuit, I still have to come back through the 1 and 2 to come back into the negative terminal. Correct? So it is still the same thing. That means it is still 1 parallel with 2, and then I add with 3 parallel with 4. Okay, so whichever way you look at it, you still get the same understanding of how the current will flow. All right, and that adds up to 2.38 ohms. Okay, so that is how you get the answer over here. Okay, so for this question here, okay, supposed to find VL, and you're already given a hint saying that you should use node voltage analysis method. So node voltage analysis is basically coming up with an equation, all right, that uses information that we have, all right, to represent nodes, and then using those nodes you come up with the equation that can help you solve the unknown. Okay, so since this is VL and all these are connected together, each of these points here is also VL. Each of these points here is also VL. Okay, so this point here is 10 volts higher than this point over here, correct? So I can write this as VL minus 10. Okay, because 10 volts higher than this, I'll get VL. So VL minus 10, I plus 10, I'll get VL here. So same thing over here. I can write this as VL minus 8. And I can write this as VL minus 6. All right, so once I get these 3 points, all right, so the expressions that we get involve, okay, if you look at all the examples, involves Ohm's law, correct? That means we try to find the voltage difference across a resistive component and use that to define a current, all right? And then we take all the currents going in or going out, all right? Either a node or super node. All right, so in this case, what we can do is, since all these points are connected together, we can just treat them as one super node over here. Okay, so the expression you will get is VL minus 10, all right, over 1 plus VL minus 8 over 2 plus VL minus 6 over 3 plus VL over 4 equals to 0. Okay, then from there you can calculate your VL to be 7.68 volts here. Okay, so the whole idea of node analysis is you use information given to represent some voltages, which you can then use to form current equations. All right, and these current equations, you then apply them to a node or to a super node, and then you solve the unknown. All right, so that is the whole idea. All right, so that is what we have done here. Okay, so for this question, so this is the follow-up. So after you do it, you get VL is 7.68. So this is 7.6. So this is 7.68, 7.68, and this is also 7.68. All right, so with this, you can see that the 6 volt source, so this is 7.68, this is 6 volt, means this current is actually going down. All right, so the current flowing in this branch, all right, is 7.68 minus 6 divided by 3. So that is the current flowing in this branch here. And that will give me 0.56 ampere. Okay, and in terms of the power, you say power is VI. So it is 6 volt multiplied by 0.56, which will give me 3.36 watt. Okay, so it's consuming a power of 3.36 watt because current is flowing in to the source over here. Okay, so let me go on to the next question. So in this, we have a load resistance RL to be placed across the nodes A and B in the circuit. Okay, so there's supposed to be a load resistance, but it's not there. And the objective is to draw maximum power. So as I mentioned just now, the moment you see this thing maximum power transfer, you automatically know it is Thevenin's equivalent. Alright, so what is the maximum power that can be utilized by the load RL means you are effectively being asked to find the Thevenin's equivalent circuit. Alright, so the Thevenin's equivalent circuit means, okay, so let's look at it from the voltage perspective first. So the VTH, so if I look at it over here, the voltage here is the voltage across these 2 points, which is the same as the voltage over here. Alright, because this A is the same over here, is the same over here. So here I can see that I have 8 ohm and 8 ohm in parallel, which will give me 4 ohm. So if I were to redraw it, it's 10 volts plus 4 ohm and then followed by 1 ohm over here. Okay, so this voltage across AB is the same voltage here, A and B over here, which means it's the voltage across the 4 ohm resistor. So it is 4 over 5 times 10. I'm using voltage divider rule. Okay, so I'll get 8 volts. Okay, for Thevenin's resistance, okay, since you imagine that now I put a supply here and this one is short circuit. So if that is short circuit means the current is flowing into parallel 1 and 4. Okay, so the RTH is basically 1 parallel with 4, so you get 0.8 ohm. Okay, so the final circuit will look like this. You have 8 volts, okay, 0.8 ohm. And in order for me to do maximum power transfer, the RL must also be equal to 0.8 ohm. Okay, so you just find the power, okay, using either I square R or V square R, you will get 20 watts. Okay, so the main thing is, as long as you see maximum power, okay, the direction is towards Thevenin's. All right, so that is the idea you must have. Okay, so let's look at this. So here we have a circuit. Find the value of resistance X. Okay, so we are given that the voltage difference between B and D is 1 volt. So this voltage difference here is 1 volt. Okay, so how do we solve this? So the important thing is, as you can see, there are no other components here, which means that the 6 volts of the supply is the same 6 volts you see here. So if I look at this, C and A. So if I draw A here, okay, and C. So between A and C, I will see the full 6 volts here. Okay, so this is 1, this is 3, this is 2, this is 6, this is 4, and this is X. So this is my B, and this is my D. So if I apply the voltage divider principle, okay, the voltage at point D is what? 4 over 6, right? Because this is 4 ohm, this whole thing is 6 ohm. So 4 over 6 times 6 volts, I will get 4 volts. Okay, so the voltage at point D is 4 volts. And I know that VB is 1 volt. That means VB minus VD. So VB is higher than VD by 1 volt. So if this is 4 volts, this has to be 5 volts. Correct? Because the difference between VB and VD is 1 volt. Okay, so that is what we know. Now, since we know that the voltage here is 5 volt, I can find the current here, alright? So the current through this two resistors here is 5 volts divided by 10, which is 0.5 ampere. Okay, because the voltage across this point is 5 volts. Okay, so the current is the voltage difference divided by the resistance, correct? So 5 over 10 is 0.5 ampere. And since resistor X is in series with these two resistors, it is the same 0.5 ampere that goes in here. Okay, so this 6 volts, like I said, if you look at the whole circuit looks like this. Correct? That means the full 6 volts of the battery supply appears across two parallel branches. Correct? And the two parallel branches are this branch, AC this way, and AC the other way. So that's why the voltage drop across 1, 3, and 2 add up to 6 volts. The voltage drop across 6, 4, and X also adds up to 6 volts. They are both parallel, and there is no other component here and here. That means the full 6 volts appears for these three resistors and appears for these three resistors. Okay, so since we have calculated that the current is 0.5 ampere and this branch, all these are in series, the same 0.5 ampere also goes through the X, resistor X. All right, and since we know that the total voltage is 6 volts, if 5 volts already has dropped across this 6 ohm and 4 ohm, the remaining is only 1 volt here. Okay, so we know that the voltage drop across here can only be 1 volt. Okay, so by Ohm's law, okay, 1 volt is equals to IR, so 0.5 multiplied by X. Okay, then from there you'll get X is 2 ohms. Okay, why is the current 0.5 ampere? Okay, so because we know VB, correct? So if you look at it, okay, we want to draw it. This is VB, all right, and VB is 5 volts, correct? And the two resistors here are 4 and 6. And then this is going back to the ground already, the negative, correct? So the current through here will be 5 volt over 10 ohm. Okay, it's the same thing is your Ohm's law, right? You can take the voltage drop across any resistive components, all right, and relate it to the current. So that's how you find out that this current is 0.5 ampere. Okay, so you just look at point B with respect to point A, and point A is ground. Okay, so from this you'll get your X, which is 2 ohm. Okay, so let's go on to the, let me see. Yeah, so the voltage at B is 5 volt with respect to ground here, all right? So whatever, so since we know that the whole branch here is 6 volts, all right, if 5 volts drop is happening at point B with respect to A, then the only remaining voltage left is 1 volt. So that's why we know that the 1 volt is the one that will appear across the resistor X. Okay, because point C to point A is 6 volts. Okay, so if you look at the whole thing, okay, point C, okay, all the way down to point A, this whole thing is 6 volts. Okay, so now I have X, 4, and 6. So I have X, 4, and 6. Okay, so if I know that this point here, respect to ground, is 5 volts, so what is left here? It's only 1 volt. Okay, so let me go on to the next question, question 12. So in question 12, what is the value of the current I1? Okay, so the current of I1 here. So this is again something similar to what we saw just now, where you can see that there is a common sort of point between the positive and negative of two supply without any component in between. So this sort of gives you an idea that this circuit and this circuit can be treated separately. All right, so this sort of tells us that this part of the circuit here, the 20 volt and 3 ohm, actually we do not need to factor in our analysis. We can just look at this. All right, so this is treated like a common point, all right, or a common reference for both the two separate circuits. So in this case, we can just treat or focus on solving only this left-hand part of the circuit over here. Okay, so we are asked to find the current I1, all right. So this current I1, as you can see, you apply ohms, you apply your resistance principles, you simplify this, okay, so you get 10 volts here, okay, 30, 20, okay, 8, all right, okay. So I mean, if you look at it, another easy way to redraw it to make it more easier to see is if you imagine I draw it this way, okay, I draw it this way, and the other part of the circuit is like this. Okay, so you can see I can sort of clearly separate this circuit and this circuit. All right, and if you, I'll explain a bit more tomorrow. But okay, if you look at it, okay, you actually see that no current flows in through this branch here. Okay, so that is how we can sort of separate out both the circuits. Okay, so as long as you can create like a clear separation between one source and another source, all right, through a line like this, then you know that you can actually separate it. So because this is a short circuit line, right, this point here to this point is a short circuit line. So which means that I can sort of close the loop here separately from this loop over here separately. Right, so that is what I'm doing. So this point here is one part and this part is another part. So I can actually treat it as two separate circuits. Okay, because on my left hand side I can close the loop, on my right hand side I can also close the loop. Okay, so that is basically how you can sort of separate out the circuits to know that I only need to focus on this part of the circuit for my analysis. All right. Now for the analysis part, okay, if you do the resistance simplification, so 20 and 30, you will get 12. These two are parallel, correct? And then you have 8. Okay, so this is what you get. Okay, so the current, okay, you will get is I is 10 by 20, which is 0.5 ampere. Okay, so as you can see, the 0.5 ampere is current flowing where? In this direction. Right? So rightfully, the current flowing through the 8 ohm resistor is supposed to be in this direction. Okay? But the arrow that is drawn is in the opposite direction. Okay, so now your answer has to be with reference to the arrow that has been drawn. So if the current in this direction is 0.5 ampere, then I1, which is in the opposite direction, is supposed to be negative 0.5 ampere. Okay, so that's why the answer here is D. Okay, so you need to reference back based on the answer that you get and relate it to the arrow that is already drawn. Okay, so in this case, the arrow is drawn in the opposite direction. Okay, so from the circuit analysis, we know the current is going in this direction, okay, but the arrow is drawn in the opposite direction, so that's why you have to put a negative in front. Okay, so that's why the answer here is part D. Okay, so let me go on to the so the whole idea is if you can separate out and draw a closed loop between one part of the circuit and another part of the circuit, then you can consider them as separate parts of the circuit which you can analyze them individually. Okay, so let me, so each part of the circuit need to have a voltage source. Okay, so that then only you consider them as two separate or different entities, correct? And then you treat them separately. If you don't have any voltage source, then it's all part of one circuit. All right, then you need to take into account everything. Okay, so let's go on to this question here, question 13. So in question 13, what is the Thevenin equivalent circuit as seen by the 40 ohm resistor? All right, so again, as before, we open up this. So what you get is 160 volts here, 10, 20, 100. Okay, so you're supposed to find the Thevenin's equivalent. All right. So the first thing is VTH. So the VTH is what is the voltage seen here. Okay, so the voltage seen here is the same as the voltage seen here. All right. Okay, so this point and this point are the same. So this is VTH. Okay, so let's call it VT. Now, how do you do this? All right, so you can use Ohm's law. All right, you can, because you can say that this is 160 volts. So this point here is 160 volt. This point here is 100 volt. All right, so I can define the current flow I to be equals to 160 minus 100 divided by the total resistance, which is 30. Okay, because no current is flowing here. So if I just apply Ohm's law between these 2 points, so I know the voltage difference between the 2 points, I know the resistance, so I know the current. All right, so this current will be 2 ampere. So if the current is 2 ampere, the voltage drop across here, all right, will be 160 minus 2 times 10. So it will be 140 volts here. Okay, so VT here will be 140 volts. Okay, so VTH is 140 volts. Okay, so that is your VTH, and then your RTH is, you redraw it now. Okay, so this is your A, this is your B. Okay, so the 10 ohm resistor is here, and a short circuit here, 20 ohm, and this is a short circuit. Okay, so the voltage sources are short circuit, and between A and B, like I said, you imagine you place a voltage source. All right, so when I place a voltage source, when the current comes out, what will happen? At this point, it will split into here and here. All right, the current through this branch will come back here. When the current goes through here, at this 20 ohm, what will happen? Okay, at this node here, what will happen? The current will see that there is two pathways, correct? One is this, and the other is the 30 ohm. All right, and the current will always take the easiest path. That means if there is a short circuit path, it will always take the short circuit path. All right, it will bypass anything else. Right? You will always take the easiest path. That means effectively I do not see this 30 ohm at all. Okay, I do not see this 30 ohm. The current comes out only goes through the 10 and the 20. Okay, so and since it's split into 10 and 20, the RTH is 10 parallel with 20, which is 6.67 ohm. Okay, so your VT is 140 volts, all right, and your RT is 6.67 ohm. Okay, so that is how you derive the Thevenin circuit for this. Okay, so let me go on to the next question, question 14. So question 14, for the circuit shown, the switch has been closed for a long time and the current measured by the ammeter is 1 ampere. All right. So at time t equals 0, the switch is open. So what will be the current reading at the ammeter at time t equals 0 plus? Okay, so firstly is when the switch has been closed for a long time, which means that the capacitor has been charged up, all right, and is now behaving like an open circuit, correct? So VC, okay, at 0 minus, all right, okay, so at t equals to 0 minus, we say that capacitor is steady state, which means it's open circuit. All right, so when it's open circuit, it has already charged up, okay, to a voltage, and in this case the voltage is capped by the component which is parallel to it. All right, so the component that is parallel to it is the 6 ohm resistor. So since I have 1 ampere going in, okay, and the 1 ampere does not see this anymore because it's open circuit, so the 1 ampere comes here. So the voltage you see here is 6 volts. All right, so the voltage at this point here that you will see, all right, is 6 volt, okay, across the 6 ohm resistor. Okay, so when I initially open the switch, okay, as what we know, the voltage across the capacitor cannot change instantaneously, so the VC would still maintain as 6 volts. All right, so what would be the current reading? So since I know that originally is 1 ampere, the voltage is IR, which is 1 multiplied by the 2 resistors. All right, because at time equals 0 minus, the closed loop is only between the 12 ohm and 6 ohm. All right, so it's 1 multiplied by 12 plus 6, which is 18 volts. So this is the supply voltage. Okay, so when I open the switch, okay, 6 volts will be seen here. So the current will be 18 minus 6 over 12 ohm. Okay, which is still 1 ampere. Okay, so the current, okay, at the time t equals 0 plus is still 1 ampere over here. All right, so let's look at the next question. So this next question is follow on to the earlier question. So we know that this is 18 volt, all right, and we know that this is 6 volts. So what would be the current reading on the ammeter at time t equals to 12 seconds? So after I open the switch. All right, so after I open the switch, all right, so there's nothing flowing here anymore, so it's only within this loop over here. All right, so since you have a single R and a single C, you can calculate tau as RC, which is 12 times 1. All right. All right, which is 12 seconds. And you apply your standard formula for your VC. All right, so VC will be VC0 e to the minus t by tau plus VC infinity 1 minus e to the minus t by tau. So what is VC0? VC0 is your 6 volts. And what is VC infinity? VC infinity in this case would be, if I let current flow continuously, then this voltage across the capacitor will grow and grow and grow until it matches the full voltage that is available, which is 18 volts. Alright, so the full 18 volts will be the VC infinity. Okay, so 1 minus e to the minus t by tau. So you put in everything, okay, so you substitute t equals to 12 inside here. Alright, the VC you will get is 13.59 volts. Okay, so this will be the voltage across the capacitor when it is 12 seconds after the switch is open. So the current will be 18 minus 13.59. That means this voltage here minus this voltage here divided by 12 ohm, which will be 0.31368 ampere. All right, so that is about this 0.37. All right, so that is your question 15 over here. Okay, then question 18. 16 and 17 are not there because those were AC related questions. So in question 18, what do you have? You have a circuit where the switch was initially open for a long time. At time t equals 0, the switch is closed. What is the voltage VAB at time t equals 0 plus, immediately after the switch is closed? All right, so if the switch is initially open, all right, there is no current flow. Okay, so if there's no current flow, current through the inductor at 0 minus is 0. Okay, when I first close the switch, the current cannot change instantaneously, so it's also going to be 0. All right, so if the current is 0, then effectively nothing flows through the resistors. All right, so the voltage across these 2 points will still be 0. Right, because the instantaneous response at 0 plus and 0 minus will always be the same. Okay, so for capacitor, voltage across capacitor at 0 minus will be the same voltage across capacitor at 0 plus. For inductor, current through the inductor at 0 minus will be the same current through inductor at 0 plus. So since the current is 0, there is no voltage seen across the resistor over here. So it's 0 volts. All right, then the last question here. If the switch is initially open for a long time, okay, at time t equals 0, the switch is closed. What is the inductor current at time t equals to 1 millisecond? So once the switch is closed, okay, the closed loop is formed, all right, and you can now apply the principles of the general equation. So the general equation says that IL is IL0 e to the minus t by tau plus IL infinity minus t 1 minus e to the minus t by tau. All right, so what is tau? Tau in this case is L by R, and we know that this has to be RL in series. All right, now if you look at it, it's 10 ohm and 10 kilo ohm. Okay, and we know that this effectively approximates to 10 ohm. Okay, so even if you use 10 ohm in the calculation, you will still get the correct answer. All right, so 10 ohm and 10 kilo ohm, you will still eventually get something close to 10 ohm, the final resistance. So the tau is given as 10 millihenry divided by 10 ohm, which will be 1 millisecond. Okay, and since the initial current here is 0, all right, so this one we can discard. Okay, so this one is 0. Now, what is the IL infinity? IL infinity is the current that will flow if I let the circuit be on for a long time. Correct? So if the circuit is closed for a long time, the inductor will behave like a short circuit. All right, so the current effectively is 10 volts divided by 10 ohm. Okay, like I said, the combined resistance is almost 10 ohm. So it will be 1 ampere. All right, so you substitute that inside here and the tau inside, okay, at t equals to 1 millisecond, you will get the current to be around 0.632 ampere. Okay, so the answer here would be B. All right, so that basically wraps up this paper as well. All right, yeah, so we have covered both the papers. Okay, so what I will do now is, okay, so for the midterm, okay, basically you more or less know what to do, what to prepare. The thing that you will send an announcement soon by today or tomorrow is the clarification process. Okay, basically what will happen is you will be given a link to a Google form, all right, where you can type your clarification questions, and this form will be monitored by all the instructors here. All right, so we will be able to monitor your questions, all right, or any clarifications that you have, and then answer them. All right, so if it is a question that we feel that everybody requires clarification, we will announce to everybody. If it's not, we will just answer through the Google form. All right, but everybody can monitor the Google form. All right, so any clarifications, everybody can also look at the questions and what is our response, if there's any. Okay, so let me answer. Okay, so for question 7, how to get Thevenin resistance. Okay, so if you look back at this, like I said, to find Thevenin resistance, once you short circuit the source, you get something like this. So you imagine how the current will flow if I were to place a voltage source here. So the current will flow here, and like I said, whether you draw it this way or the other way, both is the same. So if I draw it this way, at this point of time, okay, at this place here, current will split into 1 and 2. So we know 1 and 2 is parallel. All right. So it comes here, yes, there's a branch, but effectively to form that closed circuit, the current has to go back into the negative of the battery. All right, so it has to come back in through here. So the only way it can come back in through that is through 3 ohm and 4 ohm. All right, and since they are also in 2 separate branches, we say that 3 and 4 are parallel.
All right. So for this case, then I don't get the part whereby the current flows through the short circuit part. Like I don't get a short circuit.
Okay, so there's a short circuit part here, correct?
Yeah.
So effectively what I'm saying is when the current reaches this point here, there may be some current that may go in this direction first, all right, and some current that go in this direction, but effectively they will still come back in through this part here because there's no other way to go. Okay, so in order for us to form the closed loop, okay, even though you have a short circuit path, all right, the current will eventually still have to come back in through the 3 and 4.
Oh,
Okay,
so essentially 1 and 2 and 3 and 4 have the same current.
Yeah, one parallel with 2, all right, and 3 parallel with 4 have the same current.
I understand. Oh, so basically, if the current splits, then we can directly assume that it's a parallel array.
Yes, as long as they split, then it's parallel.
Understand. Thank you, Prof.
Okay, question 13. Okay, so why is 30 ohm a short circuit here? All right, so when you imagine I put a voltage source here, current comes out here. So at this point of time, okay, so at this place here, you see that there is 2 branches. One is through the 10 ohm and one is through the 20 ohm. As long as both the pathways have resistors, then the current will split. All right, and when it split, okay, so some current will go here. So for the current that goes through the 10 ohm resistor, when it comes to this branch, when it comes to this point here, you will see that there is a pathway to go back to the negative of the battery. So it will go back here, right, this current. For this 20 ohm current, when it reaches this point here, you will see 2 pathways. One is the short circuit part, the other is 30 ohm part. Okay, current, okay, the rule of current is that it will always take the easiest pathway. So that is why when you have 2 resistors, okay, if I have one is 10 ohm and one is 10 kilo ohm, you will see that the current through the 10 ohm is much higher, okay, than the current through the 10 kilo ohm. Correct? Because current will always take the easiest part. So the path of least resistance is always easier. All right, so 10 ohm will have, the branch in the 10 ohm will have much more current than the branch in the 10 kilo ohm. Okay, so the same thing applies here. So imagine that this same concept, I slowly keep decreasing the smaller resistance and I slowly keep increasing the higher resistance. That means over time, the current through this 10 ohm branch, if it slowly become 20, become 30, become 40, and this one become 30K, 40K, 50K, then what happens? The current through this branch will become smaller and smaller and smaller. All right, it will keep on decreasing until a point it is close to 0. Correct, and all the current will go through the branch which is getting resistance, which is getting smaller and smaller and smaller. Correct, that means from 10 ohm I go to 5 ohm, I go to 1 ohm, then I go to 0.1 ohm and so on. All right, and you will see that effectively there will come upon a time where all the current flows through this because it becomes almost a short circuit. Okay, and no current will flow through the 10K ohm. All right, so the same thinking applies here. When I have 2 pathways, one path here and one path here, the current will always take the path of the least resistance. So the least resistance of all is always a short circuit. Okay, so since the short circuit is the least resistance, at this node here, okay, all the current will take the short circuit part and go back to the source here, and no current will flow in the 30 ohm. Okay, so that is why you can omit the 30 ohm in the calculation. Okay. Okay, so in question 10. Okay, wait, let me answer this paper first, then I go to the other paper. Question 10. Okay, wait. Okay, so to find the maximum power, basically once you find RTH, the load must match RTH in order for maximum power to be delivered. Then to find the actual maximum power, you can use any formula. Okay, so let's assume you want to use V square by R. So if this is 8 volt, you know that 4 volts will appear here and 4 volts will appear here, alright, by voltage divider. So the power will be equals to V square by R. So in this case, it will be 4 square by 0.8. Okay, so question 4 in the previous paper. Let's check. Okay, so let me answer that question. Okay, so in this question, okay, from the earlier paper, when the current, okay, so when I put the voltage source here, current comes here, current will have to flow from here. And this line here is considered a short circuit, correct? So if it's a short circuit, yes, current will flow here. But what do you see? That these 2 points are the same. If these 2 points are the same, all right, when the current comes here, all right, you can imagine that all the short circuit points can be connected together. Correct. So that is why it's easier to redraw the 2 short circuit points as a single point. All right, because it is still the same point where the current will sort of separate from. All right, so the current at this point, it sees that I have one pathway through here. Okay, I have one pathway through here and I have one pathway through here. Okay, there is no short circuit part directly from the positive to the negative. All right, if let's say there was a short circuit anywhere else, all right, then you can bypass it. Okay, so for example, okay, if let's say this had a okay, I mean it would be wrong to do it, but if let's say I did a short circuit from here to here, all right, then this line would create a short circuit from positive fully back to negative. All right, you can see that this line, if I were to draw this short circuit, I will create a pathway from positive fully back to negative, which means that the Thevenin resistance becomes 0 because there's no more resistance. It's a full short circuit path. Okay, why? Because I have now created a pathway that directly connects the positive to the negative with the least amount of resistance because it's a short circuit pathway. Okay, as long as you don't have this, then you need to look at how the current will flow. Okay, the best way is to, like I said, try to redraw circuit connections in a way that you can see that, okay, if I have 2 short circuit points, I can redraw it as a single point. All right, so from this single point, I have one branch which is 120, another 120, and then another 40. All right, and then I can see that these 3 are actually in parallel. Okay, so that is the difference between this circuit and the other circuit.
Oh, Prof, but for this circuit, the thing, but wouldn't it traverse to the 4 ohms one or the 40 ohms? Yeah, wouldn't it travel through the 40 ohms since it's like a lesser path? it's lesser resistance compared to.
Yes, more current will flow here. But there will still be current flowing through 120, 120.
Then why for the previous question there was no current flowing through 30?
Because you have a direct bypass route. The short circuit in the other
I don't get what I mean by direct bypass.
that means this one is okay. Wait. Okay, so in this case, you can see that from this point here, okay, from this point over here, I can actually totally bypass the 30 ohm and go directly back to here. Okay, if let's say instead of let's assume that let's say over here there was another resistor here. Okay, if there's another resistor here, let's say 10 ohm, then that resistor would have come here. Then what would happen? Then at this point of time, I will have to split some into 10, some into 30. All right, because both also have resistance, so I have to split. Okay, more current will flow into 10, less current into 30, but there will still be a split, so 10 and 30 is considered parallel. All right, but now what I'm saying is there is nothing here. So since there's nothing here, this becomes the part of the least resistance with absolutely no resistance. So this becomes the easiest pathway to go back. So I will totally bypass the 30 ohm.
Oh, then for the previous question, the previous one, as in just now the one shown. Question 4 then, in this case, doesn't it? Oh, then in this case, even if there is, like, if there's the 150 volt connected to it, will it bypass that one, or it wouldn't? Like, if for example there was R connected to it, then would it completely bypass the R?
Sorry again, R connected to where?
R connected to the circuit. So instead of taking Tevlon, instead of removing the load, the load is still attached. Then wouldn't it short circuit? Because it is able to completely bypass the R and go to the 40 volts.
The R would have been here, right?
Yes.
So that would have become part of the series. Okay, so what you're saying is, if let's say the circuit here had another resistor over here, all right, then I would have had a situation where the imaginary voltage source is here, all right, and then I have 120 here, another 120 here, then another 40 here, and all three combine, then go into the new resistor R1 here, and then go back. So it would have been 120 parallel with 120 parallel with 40, then plus R1.
Oh yeah, I get this, but I just don't get the short circuiting. Like, how come this one doesn't work? Like for the short circuiting.
Because these 2 points are the same, correct?
Yeah.
So if these 2 points are the same, you can imagine that when the current comes here, it comes here and then it has 3 pathways to go, correct? One is...
Prof, I can't see there's no pointer on the screen.
Okay, so one way is you... Wait. Okay, so when the current comes here, it basically has 3 pathways. One is this way, all right? One is this way, and one is this way, all right? So since it has 3 pathways, then it has to split into all 3 pathways because all 3 have resistors. Okay, the only time where it can bypass a resistor is if there is a pathway in which I can I have a short circuit pathway that is in a sense parallel to one of the resistors. Okay, if I have a short circuit pathway that's parallel to one of the resistors, then it is possible for me to ignore that resistor.
Oh, I get it. Because right now, this short circuit is not exactly bypassing any resistance in that sense.
Correct. Yeah, because the current, there is no way for the current to skip any of this resistor and go. It has to go through everything. All right. So I think the confusion comes because you see a short circuit line here.
Yeah,
Right?
yeah.
Okay, that's why the confusion comes. But you have to imagine that this short circuit line, that means this point here and this point here is the same. All right, which means that when the current comes here, from this imaginary voltage source, I will have to split. All right, and when the current comes, there are three pathways. One is this way, one is this way, and the other is this way. All right, so all three pathways have resistors there, so there is no way to just skip anything. All right, but in the other case, there is actually a direct pathway from one of the node directly back to ground.
Oh,
So that is why I can actually skip that resistor.
so it must be so it must have a direct pathway to the ground. Then you can skip. Is that what it is?
Not necessarily pathway to ground. Okay, so okay, maybe.
Oh, so like for example, if the circuit remains the same, like the one in question 4, meaning that the resistance R is the resistor R is attached, then is the current able to skip resistor R and bypass resistor R and go through resistor 40? It's not able to, right?
No, because it's considered. Okay, so it's considered that these two resistors are parallel and these two resistors are parallel, correct?
Yes.
So it won't skip anything. All right. So when can you skip? Okay. So for example, if I have this 10 volt source, okay, 10 ohm. So if I draw a circuit like this, okay, if I draw a circuit like this, then what will happen? All right. When the current comes over here, all right, when the current comes here, at this point of time, you will see two branches. One has a resistor and one doesn't have a resistor. Okay. So in this case, what will happen? It will take the path of this resistance, which is this. So it will totally skip this and just go here, which is similar to what we saw in those circuits with the inductor, correct? Where the inductor or with the capacitor, because when the capacitor become fully charged, it becomes an open circuit. So no current can flow. So in this case, the same thing. But in this case, what you have is a short circuit pathway. So that it's easier for the current to flow through a short circuit path than to flow through a resistor. So all the current will actually flow through this short circuit path and skip the resistor.
Oh, so it's essentially you can only short circuit a resistance if like from point A to point B and in the middle of them there's a resistor. Then if there's an alternative path to get to point B without any resistance, then you can short circuit it essentially.
Yeah. Okay. So
Means
okay.
both the starting point and ending point must be the same to consider the short circuit.
Yeah. Correct. Okay. So okay. Let's look at this. Okay. So let's say I draw this. Okay. So if I look at this, okay, this is also another short circuit, but it's not to ground. It's across another resistor. Correct. So when this current comes in, it comes to this point here. It sees three pathways, and you see that one of the pathway is actually a short circuit. So I will take the easiest pathway and I'll bypass this. All right. So I will come here. I'll go through the short circuit and I'll go through the 30 ohm. So this 20 and this 20 are not seen by the current.
Oh, so to short circuit a current, the starting point and the ending point of all the pathways have to be the same, essentially.
Yes. So in this case, I'm doing a short circuit here across these two components. So the current that comes in will bypass these two components and go directly to the next component.
Okay, I see. Thank you very much, Prof.
Okay. Let me see. Question 10. Okay, wait, let me. Okay, so for this question here, why is it negative 6 volt? All right, this is similar to our tutorial question. If you remember, we said that the current through the inductor cannot change instantaneously, correct? So, so when there is a current flowing here, okay, so when there's a current flowing here, all right, so if the voltage at this point here, so when the current is flowing in this direction. The current is flowing in this direction. And if I suddenly close the switch, correct? If I suddenly flip the switch here, then what will happen is the the follow-up question was I open this, correct? I open this, that means this one becomes open circuit, and I close this, correct? So what will happen is this becomes the only pathway. So in that case, the current is flowing in this direction, it will carry on in this direction and flow. So as far as this resistor is concerned, current will now be flowing in this direction. Okay, this direction here. Okay, so the voltage drop across this, okay, so if the current is 1 ampere, the voltage drop across will be 6 volts in this direction. All right, and so again, the why is it positive or negative is because of the convention that is already drawn for us. Correct. So in this example, plus is already drawn on top, negative is already drawn below. So if the question asks you what is V2 at this point of time, then you have to say it is negative 6 volt because actually the 6 volts is in the opposite direction. All right, so that is why you do it this way.
Prof, then the current from the inductor is based on the polarity that it got gotten while it's being charged, right?
Yeah, correct.
All right, thank you, Professor. Oh, Prof, I've got a question for the additional questions for the node voltage analysis.
Okay. Okay, so what we'll do now is this, okay? So it's already going to be 5 o'clock. All right. So let me just follow up and close this first. All right. So tomorrow's session, the tutorial session, we still have as per normal. All right. That means you all still log in. Those who are presenting will present. The rest of you still need to do your critique analysis. All right, and submit your critique. Once that is done, okay, that means the first 1 hour is done. Then the second 1 hour is just for you all to ask questions. Okay, if there are no questions, you all are free to log off and go. All right, if there are questions, I will still be there and you can clarify anything you have with me. All right, so for now, it's already going to be 5 o'clock. Those of you who want to log off, all right, you can go ahead and log off. All right. Any questions I can still answer for a while more. All right, then I will also have to log off and you can finish up the clarifications tomorrow. Okay.
Hi, Prof. Sorry, can I just ask a question? It's like,
Yeah,
Is it that you say the current flows in this way? I think this is super unintuitive. I mean, so the follow-up question is when a switch change to this part, right?
Mm.
And then I don't understand why it's negative 6 volts. I thought it's 6 volts, right? But
No, it
you
is
say, yeah.
it is 6. Okay, so basically when the switch here at the top is open,
Yeah.
all right, and the switch over at the right here is closed, then
Yes.
you are now creating a pathway in this direction, right? In the anti-clockwise direction.
Right, but
Because the
correct.
current through the inductor was going downwards, correct?
But I thought that because the switch is open at the top here, right, and because there's no current powering through the circuit here, and so the inductor acts as an open circuit. Because there's no build-up charge here, I'm not sure.
Correct, but the current, yeah, is considered open circuit, but because there is current flow, for inductor, the current flow through the inductor cannot change instantaneously. It has to decay. Correct. So the initial current that was flowing, which was
Okay,
1
sorry, because
ampere.
when the switch is over here, right, when the switch is open, there's totally no current flowing through at all, right? Because the switch is over here.
Yeah, so correct. When the switch is open, so this part no current, but the inductor's current cannot change instantaneously. It's not like the resistor. Alright. Resistors one is immediately on or immediately off, correct? But for inductor, the inductance current cannot change instantaneously. So the same 1 ampere will continue to flow, but since it was flowing down, the closed loop part is in the anti-clockwise direction.
Oh, so there's still current flowing through this part.
Yes.
But this part there's no current flowing through it.
Yes.
Oh, okay. I see. But before that, how can the inductor be powered up? Because since there is really no power going
It's
through.
not considered power, but the current flow will still be there because in steady state it's behave like a short circuit. Correct. So since it behaves like a short circuit, we do not look at it from the voltage perspective, we look at it from the current perspective.
Oh, right, okay. Okay, just one last question. So when the question say emitter was 1 ampere, right? 1 ampere over here, is going to left or to the right? Because
1
emitter
ampere
is
in this case is, that means based on the current flow of the circuit here, that means it's going from the left to the right.
Yeah, okay, I see. Okay, thank you.
Okay.
Oh, Prof, regarding the question, let me see. Just now, the one with the inductor one, I thought that the current is flowing in the other direction.
Current is flowing downwards, correct?
Yeah, for question 15, I believe. Yeah, cause isn't not question 15, I'm not sure which question. The inductor one. Let me see. Question 10 for the 2019, I believe.
Yeah.
Yeah. Isn't the current flowing from the top down from the inductor? Then shouldn't the current be flowing the opposite direction when the switch is closed?
No, so that's the principle is that the current cannot change instantaneously, correct? So it will carry on flowing in the same direction it was flowing when there's a sudden change. So when I first flip the switch, it was flowing downwards, it will carry on to flow downwards.
Oh, so as time pass, would it change the direction? Cause there's still a voltage that's being charged.
Okay, so as it decays, it will just die off by itself. So you will not see any change in the direction of the current flow.
Oh, it's not decays. It's because there's still a voltage. There's still battery being attached.
No, in the question, they are basically saying that there is that part of the circuit is disconnected.
Understand? So when it closes, then the overall voltage across the inductance would match that of the 6 ohms parallel to it, right? If the switch is closed.
If the switch is closed, you mean the, no, okay. So when the switch is closed, all right, it will,
Because now the question is asking at time equals 0, the switch is closed. Then what's the voltage at time plus?
correct, because when it is already been, so at before time t equals to 0, it is already a short circuit, correct?
Yes.
So the short circuit would have already caused all the current to be flowing from the source through the inductor.
Yes.
Mm.
But then when they close the switch, isn't now the inductor in parallel with the 6 ohm resistor? Then as a result, the inductor's voltage will be forced to be that of the 6 ohm voltage. Be that of the voltage across the 6 ohm.
No, because the inductor is now behaving like a short circuit, means there is no voltage drop across it. It's 0.
Means even when you close the switch for a long time.
You mean after you close the switch for a long time?
Yeah. Then
Okay, if you already close the switch for a long time and the first part of the circuit is disconnected, then the current would have discharged fully, correct?
oh wait. Yeah, I get it.
Mm.
What I meant was, but the circuit is still being connected. For question 10 of the of 2019 to 2020.
So you are saying that the switch is closed?
Yeah.
Uh,
Means everything is as per normal, just that the switch is closed.
if everything as per normal and the switch is closed,
Then wouldn't the voltage across the inductance be that of the 6 ohms over time, like the end state, the
at the
steady
end
state?
state, you will still be 0 because your inductor is still short circuiting the 6 ohm resistor, right?
Oh, so it will not change once it reaches a short circuit, in that sense.
No, because at steady state, your inductor is already a short circuit, correct?
Yes.
That means even if I close the switch, okay, at t equals 0, all right, I'm now creating two pathways. One is a 6 ohm resistor, the other is a short circuit.
Oh, so it is only fixed to 6 ohms is before it reaches short circuit.
Yeah.
Then it will be stuck. Then the voltage will be forced to be that of the 6 ohm voltage.
Okay.
In a sense.
No current is going to flow through the 6 ohm resistor unless you break the circuit on the other side.
Okay.
Because as long as the circuit is closed on the other side, the inductor will behave like a short circuit, which means that that line will bypass the 6 ohm resistor.
Okay, I get it. But then I still don't get why is it negative 6 volts? Because isn't the top 6 volts and the bottom 0? The bottom is grounded. What? So isn't the voltage negative? I mean voltage 6.
So because the current has been flowing in from top to bottom, correct?
Yes.
So if let's say now I open the left hand side of the circuit and close the right hand side of the circuit, the current that is now going to flow in is going to be anti-clockwise inside the right hand part of the circuit.
Anti-clockwise. But isn't it still clockwise?
No, it's
I
anti-clockwise.
don't get why it's I don't get why it's anti-clockwise.
Okay, wait. Okay, so this is the anti-clockwise, correct? Because it's been going down, correct?
Yes.
So it is now going to carry on in this direction if let's say this part is now open.
Oh, okay.
So it's not going to go in this anti-clockwise direction. So that's why it's considered negative 6 volts.
Oh, so in time, would the current go the other direction?
No, it will just carry on in this direction, it will decay.
Oh, means the inductor's direction will not switch.
No.
The current flowing.
No, it won't change.
Then in what circumstances then would the current change?
It will not change unless you now try to when it is in the transient state, you make it flow in the opposite direction, then it will change.
What do you mean by transient?
That means if let's say now I connect my V1 the other way around, then it will go the other way, correct?
Oh. So but by itself, when you disconnect the inductor from the when you disconnect the inductor and the 6 ohm resistor from part of the circuit, the current will not change.
No.
Oh, okay. I think I got it already. Thank you. Oh, then regarding the additional
Yeah, maybe we'll discuss
questions.
tomorrow.
Oh, no problem. Thank you.
Okay. Thank you.